Three animal handlers are using cables to keep a tranquilized, abominable snowman or yeti at rest at the origin below. The yeti is on ice, so he's experiencing negligible friction. Now, handler A in the upper left is pulling with a force of 200 newtons, so the tension in this cable is 200, and that would be the tension in cable A. Let's see, there's an angle theta A of 45 degrees right here. And handler C at the right is pulling with 300 newtons. So let's write that in. At a standard position angle of 0, which just means pulling in the positive x direction. Because for standard position, it's just 0's over here, 90, 180, just like it is in math, and then 270 down here. And let's see, we want to find the tension that handler B is pulling with and what angle they're pulling at. Alright, so with this type of problem, it's all about having a balance of forces. So you may want to redraw the situation. I'll just put a point in the middle to represent the yeti. It's gonna feel pulled to the right with 300 newtons. I'll call that FC. And it's getting pulled to the upper left with 200 newtons. And it must be being pulled down and to the left with some unknown force. Now what we want to do with forces that are at weird angles to each other like this is we want to resolve them into the vertical and horizontal components. So our axis is aligned such that the positive y is up and to the right is positive x. So see, the force of A is not in alignment with x or y, and that's the problem for vector mathematics. So you want to get this vector to be resolved into its components. So you want to take and make a vertical component which is just as tall as that vector's head is, and that'll be called FAY. Then over here you want to do the same thing, and we'll call that FAX. But you go as far left as that vector's head does. It should be that you created a rectangle with your components. And you want to do the same thing with the other force FB, which is not like in alignment with them either. So you want to do a vertical component, FBY, and a horizontal component, FBX. Now what you do is you get rid of the vectors that you had originally, and you just redraw it using the components that you've just newly created. So we have that, we have this, and this, is this, and that. Now, this is a Newton's first law problem where we're in translational equilibrium for this yeti. Translational equilibrium implies that the sum of the forces is 0. Now, that statement alone is like a statement about vectors where the force could have an x, y, and even z component. So that means that the sum of the forces in the x is 0, and the sum of the forces in the y direction is also 0. And that's what we use to solve it. So you want to start to like make an equation out of the x and y. So you might do the y first, because you've got only two forces in that dimension, Fay and Fby. So you could say that Fay plus Fby has to equal 0. That just says that the sum of forces in the y direction must be 0. And they can hold a negative or positive sign inside them. That's the idea with putting the y subscript on there. It means it's relative to the y-axis. So ones that are pointing up, they'll be positive, and ones that are pointing down are negative. All right, so to solve it, you might say, okay, this is a 45-degree angle here, they said. So we can find out what Fay and Fax are numerically. So Fay is going to be Fa times the sine of theta A in standard position. So there's a lot to that. Okay, so first of all, Fa is the strength of the tension in that cable. It's 200 newtons. But the theta is tricky. Standard position is always measured from the positive x direction. So you start on the right. So start here, go all the way around. So yeah, that'll be 135. Perfect. Now you don't have to use standard position angle in order to find the component. Some people don't do it that way. Some people will just take the triangle there and they'll make their own like SOHCAHTOA triangle. So they'll know that this is 45. And then they'll know that the hypotenuse is 200. So they'll say, okay, cosine 45 equals the adjacent over the hypotenuse, you know? And so that's another way of finding it. So it's just up to your preference of like which way you prefer, standard position or not, you know? Okay, so 200 sine 135 comes out to 141. So this is 141 newtons. Okay. So what that implies is that Fby must also be 141 newtons. So you plug it in, 141 newtons plus Fby equals 0. Then you solve to find that Fby is negative 141 newtons. So that helps us find one of the components that we need for that rope B. So now you have to do the harder dimension, which is the x dimension, because there's 3 forces in that dimension. We have Fc equal to 300, so at least we know that. But we don't know the blue and the red. So let's find the blue first. That would be Fax. So Fax can be Fa cos theta. Alright, so it's going to be 200 cosine of 135. Comes out to negative 141 newtons. Alright, so now we still need to find Fbx, but it's the only thing that's unknown now. So what you want to do, write one more equation saying that the sum of forces in the x direction is 0. So you would say Fax plus Fbx plus Fcx is 0. We'll have negative 141 for the FAX because you want to keep track of the signs. FBX is unknown, and FC is 300. Therefore, this is solvable for FBX. FBX is 159 newtons, but it's negative. Alright, so now we have the y component of FB and the x component. And we can put them together now and reconstruct what FB is. So we have negative 141 newtons, negative 159 newtons. So they will combine to make a single vector FB. And it should be that it makes a rectangle. And now to get the magnitude of FB, you take its components and you do this. The magnitude of FB is going to be the square root of the squares of its components. Yeah, so we'll just want negative 159 squared plus negative 141 squared, 213 newtons. And then we should also give a direction and standard position. So for standard position for that vector B, the person's pulling that way. So we actually want to measure from the positive x direction all the way around until we hit the vector. That's going to be theta B in standard. So the first thing we have to do though to find that standard position angle is find what's called a reference angle. The reference angle is the angle it makes with the x-axis, like the smallest angle it makes with the x-axis. I call that beta. So let's find beta. There's a formula for it. Its beta is the tan inverse FBY over FBX. So that'll be tan inverse of 141 over 159, 41.6 degrees. So we know beta now, 41.6. And then we just have to, since we're in the third quadrant, that's the direction that the vector is pointing, we just want to add 180 to the 41.6 to get that full angle. So our theta B in standard position will be 180 plus beta, which is 180 plus 41.6. So theta B is 222 degrees.